In number theory, two integers A and B are said to be relatively prime, mutually prime, or coprime if the only positive integer that evenly divides both of them is 1. That is, the only common positive factor of the two numbers is 1. This is equivalent to their greatest common divisor being 1. The numerator and denominator of a reduced fraction are coprime. In addition to and the notation is sometimes used to indicate that A and B are relatively prime. For example, 14 and 15 are coprime, being commonly divisible by only 1, but 14 and 21 are not, because they are both divisible by 7. The numbers chapter 1 and -1 are the only integers coprime to every integer, and they are the only integers to be coprime with 0. A fast way to determine whether two numbers are coprime is given by the Euclidean algorithm. The number of integers coprime to a positive integer n, between 1 and n, is given by Euler's totient function phi. A set of integers can also be called coprime if its elements share no common positive factor except 1. A set of integers is said to be pairwise coprime if A and B are coprime for every pair of different integers in it. Properties. A number of conditions are individually equivalent to A and B being coprime. No prime number divides both A and B. There exist integers x and y such that x plus b equals 1. The integer b has a multiplicative inverse modulo A. There exists an integer y such that by 1. In other words, b is a unit in the ring Z, Arizona of integers modulo A. Every pair of congruence relations for an unknown integer x, of the form xk and xl, has a solution. As stated by the Chinese remainder theorem, in fact the solutions are described by a single congruence relation modulo ab. The least common multiple of A and B is equal to their product ab, i.e., LCM equals ab. As a consequence of the third point, if A and B are coprime and B are BS, then RS. That is, we may divide by B when working modulo A. Furthermore, if B1 and B2 are both coprime with A, then so is their product B1 B2. This also follows from the first point by Euclid's lemma, which states that if a prime number P divides a product BC, then P divides at least one of the factors B. As a consequence of the first point, if A and B are coprime, then so are any powers AC and BL. If A and B are coprime and A divides the product BC, then A divides C. This can be viewed as a generalization of Euclid's lemma. The two integers A and B are coprime if and only if the point with coordinates in a Cartesian coordinate system is visible from the origin, in the sense that there is no point with integer coordinates on the line segment between the origin and, in a sense that can be made precise, the probability that two randomly chosen integers are coprime is 6 pi 2, which is about 61%. See below. Two natural numbers A and B are coprime if and only if the numbers 2a-1 and 2b-1 are coprime. As a generalization of this, following easily from Euclidean algorithm in base n greater than 1, coprimality in sets. A set of integers S equals a1, a2, and can also be called coprime or setwise coprime if the greatest common divisor of all the elements of the set is 1. For example, the integers 6, 10, 15 are coprime because 1 is the only positive integer that divides all of them. If every pair in a set of integers is coprime, then the set is said to be pairwise coprime. Pairwise coprimality is a stronger condition than setwise coprimality. Every pairwise coprime finite set is also setwise coprime, but the reverse is not true. For example, the integers 4, 5, 6 are coprime, but they are not pairwise coprime equals 2. The concept of pairwise coprimality is important as a hypothesis in many results in number theory, such as the Chinese remainder theorem. It is possible for an infinite set of integers to be pairwise coprime. Notable examples include the set of all prime numbers, the set of elements in Sylvester's sequence, and the set of all Fermat numbers. Coprimality in ring ideals. Two ideals A and B in the commutative ring are called coprime if A plus B equals R. This generalizes Bezout's identity. With this definition, two principal ideals N in the ring of integers Z are coprime if and only if A and B are coprime. If the ideals A and B of R are coprime, then AB equals AB. Furthermore, if C is a third ideal such that A contains BC, then A contains C. The Chinese remainder theorem is an important statement about coprime ideals. Probabilities. Given two randomly chosen integers A and B, it is reasonable to ask how likely it is that A and B are coprime. In this determination, it is convenient to use the characterization that A and B are coprime if and only if no prime number divides both of them. Informally, the probability that any number is divisible by a prime is, for example, every seventh integer is divisible by 7. Hence the probability that two numbers are both divisible by p is, and the probability that at least one of them is not is. Any finite collection of divisibility events associated to distinct primes is mutually independent. For example, in the case of two events, a number is divisible by primes p and q if and only if it is divisible by pq. The latter event has probability 1, pq. If one makes the heuristic assumption that such reasoning can be extended to infinitely many divisibility events, one is led to guess that the probability that two numbers are coprime is given by a product over all primes. Here zeta refers to the Riemann zeta function. The identity relating the products over primes to zeta is an example of an Euler product, and the evaluation of zeta as pi 2/6 is the Basel problem, solved by Leonhard Euler in 1735. There is no way to choose a positive integer at random so that each positive integer occurs with equal probability. But statements about randomly chosen integers, such as the ones above, can be formalized by using the notion of natural density. For each positive integer n, let Pn be the probability that two randomly chosen numbers in a coprime. Although Pn will never equal exactly, with work one can show that in the limiters, the probability approaches. More generally, the probability of k randomly chosen integers being coprime is 1, zeta, generating all coprime pairs. All pairs of positive coprime numbers can be arranged in two disjoint complete ternary trees, one tree starting from, and the other tree starting from. The children of each vertex are generated as follows: branch 1, branch 2, branch 3. This scheme is exhaustive and non-redundant with no invalid members.